Just while we're introducing, or last time we looked at differential equations, kind of an introduction to them. While we're on that subject, we're going to look back at exponential growth and decay, something you looked at in grade 12 math, and you modeled things that way with what you had available to you in grade 12. Now that you have differential equations, you can look at a different model for exponential growth and decay. The first concept, I guess, to understand before you write any kind of differential equation for this is exponential functions are such that you have some starting population. Remember what an exponential function looks like? Like maybe you have 1,000 people in a town or 1,000 something, and it's growing exponentially. Growing in a linear fashion is straight line like that, right? Regardless of how many people are in the town, the rate's always the same. Linear means the rate is constant, right? No matter where you measure the rate, even if you let this go on and on and on here and up, the rate is always the same. That's what a straight line is. Measure the slope, it's always the same. An exponential function, it starts to curve, right? It curves up. The farther along you go, the steeper the curve is, right? If it's exponentially growing. Another way to define it or to look at it here is the slope here is proportional to the amount. Okay? The higher the amount is, the more the slope is. All right? So as this population goes up here, the slope increases. Does that make sense? If you think about a population of a town or bacterial growth or anything like that, the larger this number is, the faster the rate of growth is going to be, like number of people per day, number of bacteria per day, or whatever you're going to measure it in, right? The rate of, the slope of this would be whatever you're measuring time in here, days or weeks or something like that. And this is population of whatever you happen to be looking at. This is going to be individuals, bacteria, people, whatever per day. The slope is going to be those are going to be the units on the slope. The higher the population, the steeper that rate is going to be. Okay, so that's what this says here. The rate of growth for something that's exponential. Okay, the rate of change of a quantity is directly proportional to that quantity. What does it mean to be directly proportional? If two things are directly proportional, one thing goes up, the other thing goes up, and it can be a constant multiple, right? If this quantity is 1 and this is 4, then this is 2 and this is 8 and so on, right? One's a multiple of the other. The way you write that in general is you say y is k or something, some constant times x, whatever you want to make that constant into, but some number, I don't know if you've ever heard the word directly proportional, but that's what it means, right? Something that's directly proportional is this quantity are connected by being multiplied by something here. If we're going to write this is saying the rate of change of a quantity is directly proportional to that quantity. So if we're going to use, let's say, P for population, and T for time, right? If all you know about a situation is the rate of change is proportional to that quantity, we're not going to write a function right away for P, but we can write a differential equation because we don't know something about the population itself. We know something about the rate of change. How do you write the rate of change of population as compared to time in this situation with those variables? dp dt, right? And it doesn't say that it's equal to that quantity. It says the rate of change of a quantity is proportional to that quantity, so it's some constant times that quantity, which I'll just put a k there for now, I guess. Okay? This is a differential equation that expresses that fact that's highlighted in yellow there. The rate of change of a quantity, maybe let's color code it here. This is the rate of change of that quantity we're talking about. Directly proportional to, some multiple of this other thing, right? That quantity, which is that, right? That differential equation expresses the fact that the rate's proportional to the amount that's there, right? The more people there are, the higher the rate's going to be, right? In a city that is 1 million people, the growth rate is probably whatever it happens to be. It's going to be a lot more than a city that has a very small growth rate. Okay, you could of course put P prime equals K times P either way, right? Whichever way you want to express the derivative. But that's all that is saying. You can solve that differential equation and you'll come up with a model that looks a lot like what you used last year, except it'll involve something else. Last year in grade 12, you modeled population growth and things. Like if you had a question like this in grade 12 and it was 1,000 people growing at 5% per year, how would you model it with grade 12 math? You might have said the population is 1,000 times. Where's the variable, first of all? The variable is, it's an exponential function. The variable is up there, right? So what would you put in here for the rate, though? 1.05. This is a slightly different model than what we're using here, right? Here we're assuming it's continuously growing, whereas this other model here assumes that sort of all the people come at the end of the year, not continuously growing. This is an okay model for it. There's nothing wrong with that, but this, what we're looking at right now, is probably a better model. Okay? So this is grade 12. Just reminding you of that. It's going to look very similar to that, except we're going to start with this and work from there. Okay? What we know here is this is saying if it's growing at 5% per year, you can put that number in here, right? The rate of change, the amount that it's growing at is 5% of the population at any time. So how can you write that? Can you just put this in here? You can put 0.05 because this is saying the rate. Not responding, that's really good. Uh-oh. You could put that value in there because rate of change is 5% of that. This is the equation that you're going to use here. Okay, you can solve that differential equation. Solving it means coming up with what P is equal to. How do you? No, well you don't have P is some function of T like this. We are starting with a differential equation. Differential equation is one that involves this derivative here. But if we want to write it as P equals some function like we did in grade 12 here, you have to solve this differential equation. As in, what do you do to this to try and solve it? If you have a derivative there, you're going to... Somehow you have to do some integration here. You have to separate the variables like we did last time, right? You need the dp on one side, and you need the dt on the other side. And then, where does that p go? Maybe I should actually move it around to show you here, right? We want this on the other side, right, like that. And don't you need this on the other side, like that? You need to have all of it's to separate the variables and then integrate both sides. You end up with that. Now I'm going to rewrite it instead of leaving it like that, of course, but that's what it is. Okay. So you can have dp equals 0.05p times dt, but that p has to be on the other side. So you could write it as 1 over p dp equals 0.05 dt. Then you can integrate both sides, right? If you integrate both sides, what do you get here? Yeah, you can go up here with this. You get ln of absolute value of p equals 0.05 t plus a constant, right? But we want to write it as p is equal to something, right? So you gotta anti-ln both sides. You gotta e both sides. You e both sides. Very, very precise mathematical language we got going here. E to the 0.05. In this particular case, again, you can leave out the absolute value brackets because this is always a positive. No, I didn't write it very well. That should be, where should my C be here? This should be clearly up here, right? And maybe even a bit smaller. That's part of that, right? You're going e to the power of everything there, right? Since it's e to the power of something, it doesn't matter what that something is, it's always going to be a positive. So you can actually just write it as that. 0.05t plus a constant up there. Oh, constant. The constant is in the exponent. Now, you could leave it like that, except that I do want you to see how it matches up with what you learned last year. There's two parts to the exponent. If you have in grade 9 or whenever you learned your exponent rules, x to the m plus n, how could you write that? Two things added in the exponent, you can write it as, except it's times, right? Uh-oh. Bad stuff is happening. X to the n. Okay.
10 minutes.